I'm Sexton. I'm talking about ASDs. So I'll just get started. I build JavaScript apps for a living, so a lot of this is applicable to actually building real apps. I do kind of nerd out on languages sometimes, but a lot of this I use in my real job. I'll even use both in my real job. Quick stats on me. These are accurate as of maybe 2 months ago, so I don't know if it's different. I apologize. Bench is definitely down. So what's an ASD? I have some options up here that we can go with. Yeah, it's D. It's actually secret option E, which is I guess it's Adam's girlfriend. She's in a sorority and it's ASD. It's I guess Alpha Sigma Tau. I know Greek letters. So it's an abstract syntax tree, which still doesn't tell you much if you're a human. This is what I think that is the best explanation of an abstract syntax tree, but doesn't fly in the programming world. So the abstract part of this is just really means that there's no rules, and that it can be any shape, size, or way that you want it. And so it's really like a way to say leave your expectations at the door because it'll make you mad. Syntax means that generally we're building these trees in relation to some sort of parsed language, but that's not always true either, so you can't really rely on that. And then tree refers to the data structure, so we're a little bit more hardened here as far as what we can do, but really all that means is that you'll probably need to use recursion. Oh yeah, that's what I wanted. Why would it do it? Anyway, let's go back here. Alright, so how are ASDs made? This is going to be important whenever you want to start hacking. And I mean that quite literally, and we can get to the details on that. Let's see what time I started. 40 minutes? Alright. So parsers create ASDs. And parsers, some people run it by hand. I generally tend to be too error prone as a human to write my own parsers, so I use parser expression generators. There's things like JSON that can do that. That has some limitations in the sense that people intentionally put limitations on their parsers so they can be faster. I generally use Peg. Peg.js is a good version of Peg in JavaScript. It essentially takes a grammar that you write by hand with a special syntax, and then turns it into a parser for that. And then you get to define what the nodes are. I'll go into details on that. So the first step is writing a grammar, which is rules about what everything means. So here's a grammar for addition-only math problems, and there's probably a lot of errors because it's a harder problem, but a very simplified version of this. So we might have some matching to do for some of our base types. We got a number is just going to be a number in a regex. Any number of digits altogether is a single number. An operator, in the case where we only have addition, is only the addition operator. And white space is white space. So it's a pretty tough regex there. Sorry for putting regex in a presentation. It was necessary. And then, since addition can be chained, you can say 1 plus 2, or you can say 1 plus 2 plus 3 plus 4 plus 5, right? You kind of have to find a way to, into a tree later, or you have to pick something that can be repeated so you can add it to the grammar to say, and this can be repeated, right? So the whole thing can't be repeated. 1 plus 2 can't be repeated because then it would be 1 plus 2, 1 plus 2, right? There needs to be a plus in there. So the right side is what can be repeated here. This happens a lot whenever you're parsing other grammars, including languages and things like that. A lot of going to be very similar to the way math works. If you think about expressions in JavaScript and things like that, a lot of times you'll be able to add things onto a single set or not. And so we define the right side as an operator, optional white space, and then a number. And then the full operation is going to be a number, white space, and then the right side operation repeated as many times as necessary. Technically, that could probably be an asterisk, because I guess just a number would be a valid addition. Maybe, I don't know, the identity addition. Alright, so this would be a very simple grammar for that. And then you might describe some node types that you generate whenever you find these different parts. So for our base types, you're going to have, you just name it a number, and then you throw the value that that number is into that object, right? So pretty simple. And then you have an operator, and in this case, the value is always going to be the plus operator. And then you have these nodes, and so now you have these pieces of these objects that represent what was in the actual string that you passed into the parser. White space, we don't care. That can go somewhere. It can be really long, it can be really short, it can be non-existent. So we actually don't even, we just throw it away when we parse, because white space is totally optional. And then for our more complex things, this is when you get into the tree. So these were more of the leaf nodes, and these are going to be kind of the tops of the tree, or kind of. So an operation right side is going to have its own name, and then it's going to have statements. Since it is, by definition, only two parts, that statements could technically be a binary tree that just has two branches, but we'll just go ahead and say that maybe in the future we define a new kind of math that has three parts there. Or we start caring about white space in the future or something. So, so you put your two base nodes inside of your right side node, and then when you build an operation, you put the number node, and then you put the list of operation right sides. And so you can tell by this right here, it's lower than I thought. You can tell that, like, in the long run, this is actually where, in an addition problem, pretty much your whole problem can be, defined. You say something, plus something, plus something, plus something, right? In a more complex language, it's not going to be so flat to where you can kind of gain that much information from a single level of the tree, but addition's pretty easy. And so this one's a little smaller, so I apologize if you can't read that. I would zoom in, but lately Chrome's been crashing whenever you do the accessibility zoom, so I'm not going to risk it. This doesn't really help, does it? Alright, so what we're looking at here is kind of what would come out the total tree, right? So you have the program, and that is 1 plus 2. Kind of the string that comes in is parsed as an operation. That operation has statements in it, and those statements are going to be a number and then a right side. And then that right side has statements in it, and that's an operator and a number. And so 1 plus 2, as an AST, would come back to you looking almost just like this. So it's not that complex. If you wanted to go through and figure out what are all the numbers that are used in this operation, was there, how many plus operations did we do? There's data that you can get out of it. It wouldn't be very interesting because I've overly simplified it. But you could do it, right? And that's really what I'm going to get into, is whenever you start parsing more complex, interesting things, you can get a lot of information out of an AST. And that can be really helpful. So later, someone writes a compiler, and in JavaScript, that wouldn't be very interesting. They would literally just take in that data and almost spit out exactly the code. Maybe they'd wrap it in an IFE or something like that. But the compiler takes the parsed AST and then it spits out executable code. So for a templating language, it will parse the actual string that is the template, turn it into an AST, and then it will compile that into a JavaScript function. And that JavaScript function usually will just be a series of object data lookups and string concatenation. So if you look at like a precompiled template from Handlebars or Mustache or something like that, that's the whole phase that's happening. You can actually jump into that phase. So things that are parsed like this, pretty much anything that is a language is parsed like this. There are a few people who are like rogue regex hackers and stuff like that. I know Rezig has the smallest template library. His is just like eval JavaScript inside of some tags, and so he doesn't have to do all the parsing and stuff, but I'm not that cool. So JavaScript and CSS are like this. Generally, you don't have access into these parsed ASTs and things like that unless you kind of do something in the middle. You could use a schema and then re-parse something, but something like Stylus and Sass and Less and newer Mustache, and just about every template language these days that wants to be fast. I have some internationalization stuff that's parsed like this, and then CoffeeScript and TypeScript and Dart all are parsed like this, and then output JavaScript or output CSS, kind of the base languages that have been reparsed and recompiled and re-executed into C. So this gives us the ability for all of these sets of things that we have access to kind of screw with some things. And that's really what I want to get to as long as everyone understands where we're at. So we have an easily traversable representation of a parse language. Easily is asterisk because it's not that easy, but in the grand scheme of things, it's not hard, it's just tedious. So we have data, and you can treat ASTs as data about the input language. So the key to a lot of what I'm going to show you is that it's also mutable. So if you know what node types go where, you can take them out and you can put new ones in, and you can reorder them, and you can kind of screw with the whole thing. So you can write things, you can add your own features to languages that you're using, essentially. As long as they can be parsed by the parser, you don't have to actually handle that stuff where you might think you do. And that can actually be great because in a world where we're compiling everything down to JavaScript, anything that we have to do at runtime is just going to cost extra bytes and extra lines of code and extra speed decreases. So anything that I know at build time, I should be able to build in or out of my application and really serve the most streamlined version of my app. And that's why it comes back into my actual job. So that being mutable really helps. So I have a project on GitHub called the Require Handlebars plugin. And it's pretty popular these days if you use Require and Handlebars, so not very popular. But it does a lot of this stuff. So this is a pretty crappy demo page, but I was going to maybe get just code it. So in this, I don't know the best way to show this to you actually. In here we have a page, and a lot of things are loaded in this page. You'll notice you have require, and then we have a main file here. Over here, we use this plugin that I wrote, and the syntax for plugins in Handlebars is HBS. So we can come over and we get this template, and then if you notice here, it's returned as a function. We can just call this function later with data. And so what does this do on the back end? First it downloads the plugin, and then it'll go grab the dependencies of the plugin, and then it'll grab some of the language dependencies, and then it'll grab the actual template, and it'll get it back as text. And so the first thing it does is it will parse it into an AST, and then it will go through that AST, and it will find everywhere that we use any variable, it'll find anywhere that we use any helper, any partial, and it will compile those into data. So I can show you what a parsed AST looks like. We can do require HBS 1. No, we can't. What's that called? Just one. I get it. So we get back a function in this case. And so in the actual, I apologize. whenever you take in a template like this, you can throw it through handlebars, like so. Get that back. And then we'll do a parse. So handlebars has a parse function. It's probably not going to work. Well, I won't do that then. You get back a. I'm going to do it. Here we go. Small screens. There we go. Okay, so you get back a tree that looks a lot like the ones that we were looking at before. And you can find the block nodes, and you can find all those things, and then you can create essentially new blocks in place of the old blocks, and build in your dependencies directly into your new templates. And so whenever all is said and done, you can run a build on this, and you have a single compiled template with all the dependencies, and you don't have to go and register your partials. You don't have to register any of your helpers. You can get metadata about variables. That's one thing you can grab from this. So we have data about what helpers are used on here. And with this information, essentially you can not have to do a lot of the tedious work. The cooler one is actually with stylus. So with stylus, you can write CSS in a nice way, and then TJ wrote a nice parser for it. And then I can come in here and pull in all of his functions that he has in different files, and then override those functions and add in my own AST injection zone. So essentially they're the same functions that they were before, except for I wrap them and kind of pull data in and out. And so in our app, we have a CSS file, and this is generated with stylus, right? So this is base CSS. And then I wrote a parser, a parser wrapper for TJ's parser, and that loads up a reversal. So what I did was took the AST that's generated from stylus, and then you can inject information about which variables show up in which blocks. And then you can extract that information later and do a reversal. So the purpose of doing this would be if you have a case where you want to quickly see results of single variable changes in stylus. You can't recompile every millisecond because stylus has a non-trivial compile step, but you can get it to work. So in this case, I want to change a variable in our app, and I want it to happen in real time. And so I didn't write any code here to directly attach to some style element on this element. I actually am parsing the stylus AST, figuring out what variable this is, and then figuring out what rules and selectors that it affects. And so this is the reversal of the entire CSS file. So if I wanted to change this variable, these are the selectors that it would affect, and these are the rules that it would affect it on. And so then I can inject a style element and just override those styles directly. And so with that, you can get kind of a live injection of all that stuff. So the last one that I'll mention is things like message switching and things like that in internationalization. We also use a lot. So whenever you have to do an internationalized app and you have switchable messages and you have to pre-compile formats and things like that for that, you don't want to have to pull in all possible strings in all possible languages in real time in your app. So you can use this kind of stuff to automatically inject compiled messages into your templates. I have a slide for questions, but I don't think I'm taking those. But grab me if you have any questions about this, and I can show you what a parsed HBS template